Welcome, everyone, to the second CloudBank Cloud Clinic in 2025. I see we have Shava joining us also. And this will be recorded, possibly reprised. The topic today is data publication, sometimes associated with the idea of science gateways. And we're presenting this on behalf of CloudBank out of the University of Washington eScience Institute, and we'll cover both the CloudBank as an organization and where that sits in the pantheon of data science supporting entities in the US. And then we'll dig into the process of learning how to implement a data system on the cloud and both publication of that data and then access to that data. So that's the general game plan, and the link down at the bottom of this title page will persist for a couple of slides. So the idea of Cloud Clinic series is to demonstrate the feasibility of a particular build path for a particular objective. The broad topic that we're working from is building data science environments on the public cloud. And the first clinic, which we had about a month ago, maybe a little bit more, is the emphasize the cost savings that you can realize, often like market, and that is important. Can be very expensive, and if we have a way of stretching our dollar by a factor of 3, that's a huge win. Today's clinic, Clinic 2, on science gateways and data publication and access, features 2 examples that I'll kind of mix together in the narrative here. First, a simple example, which is publishing and then accessing the periodic table of elements. And then a slightly more complicated example, which involves some ocean sensor data. Today's presentation will include some jargon, specifically NoSQL, serverless API, and VS Code. I'll go through these real briefly here. NoSQL is a reference to a form of database that's become very popular in the last 15 years or so. And it is sometimes expanded out to be not only SQL. So in other words, an expansion on the original SQL database architecture. The second term I have here, serverless, is worth sort of committing to memory. It refers to a transaction or the execution of code on the cloud that happens without regard to the underlying computer that upon which this code is running. And this is important for somebody who's building infrastructure on the cloud to realize that serverless exists, because it can be a really simple way of getting things done where you're not having to spend all that time messing around with virtual machines. API is short for Application Programming Interface, and it's simply a programmatic way for one computing resource to talk to or exchange information with another one. API, Application Programming Interface, is in contrast to like a human interface. And let's see, the last one here is VS Code, which is a integrated development environment for creating content that we're going to be particularly publishing to the cloud. So VS Code, think of it as an application that runs on a computer that a developer would use to, again, build the infrastructure. So a lot of this talk is about building things. I want to emphasize the non-recipe approach to thinking about this stuff. We're basically advocating for learning and using cloud technology, and there can be a temptation, for me at least, to use tutorials as recipes where I kind of am in a hurry to get to the end result. And the problem with that is that if there's a need to repeat that process or to debug it, building a context web from which one can think about and reason about and approach debugging, for example, is really helpful, but it requires kind of a non-recipe approach to the ability to pause and dig into what's going on and sort of do background research and so forth. So this abstract for this talk, I just wanted to emphasize the yellow sentence in here, which is we're supposing that You are building a data system, a science gateway, and you put some data in there, and then a month later you have a new idea about something else you'd like to do. And what's nice about what we're presenting today, what's really powerful about it, is that it is a development system that allows you to go back in and redeploy that data system with modifications that you decide on. Since it's sort of the basic premise of research that you'll be coming up with new ideas all the time. Moving on. Who's giving this talk? I am giving this talk. My name is Rob Fotlin. I'm with the University of Washington, as noted. And this talk was prepared with Naomi Alterman, who's also at the UW. We're both at the eScience Institute. And I wanted to emphasize the fact that as a non-computer scientist who's learning this technology, I'm sort of maybe a proxy for a research team that does not have computer scientists on board. And so my perspective is that of somebody learning this as kind of an outsider. I do have experience with shoeboxes, more on that in a second. And I do subscribe to the open science philosophy that sort of a rising tide, that the more facility we can build into our data systems, the more potential there is for research discovery. Okay, so very egotistically, I'm going to define Rob's first law, since I'm Rob, which is the rather obvious statement that data is never acquired in the manner in which it is used. But this creates a sort of an impedance mismatch between acquisition and use. And so that impedance mismatch is something that we can address by the cyber infrastructure or the research computing infrastructure that we choose to build. And then I want to define the shoebox problem. The idea is that I would one day say, hey, look, I found something under the desk. It's a shoebox of data tapes. Gosh, it sure would be cool to publish this data on the web for open use, because it's still got a lot of value, but how to do that. So that's the shoebox problem, or the science gateway problem. And so we'll move along into how to address that. But before I do, get into how to deal with the shoebox problem, there's going to be a multiple slide digression here on the general topic of cloud platforms for data science and how CloudBank fits into that. So CloudBank is a NSF-funded organization. The program is led by our colleagues at UC San Diego. And also there's a third group contributing at the University of California, Berkeley, and then the University of Washington is our team. And this is how we see research. We sort of see a research team as having a principal investigator, an administrator who makes sure that the bills get paid, and particularly on the cloud bills get paid. Then there are the people who are actually building the working infrastructure on the cloud, the builders. And then there are the people who come along and use that infrastructure to do research. And that includes not only the people in that research team, but also potentially collaborators and even people far away that one does not know, who still also have a use for that data interface. So the case study that we're talking about today, the second case study, there are two. The first one is the example with the periodic table, and the second one is from an ocean observatory. There are some sensors that are deployed in the ocean. They take 1 sample per second, and we want to take a look at that data. But furthermore, we're talking in this presentation about building infrastructure. We're saying, yeah, here's the steps, here's the procedure, this is the rationale for how it goes. But we don't want our colleague, another scientist somewhere else, to have to know about any of that stuff. So instead, in a perfect world, they have open up some Jupyter Notebook execution environment, write 2 lines of code, and they're looking at the data. So that's kind of the holy grail of the point of this program here. So we're kind of trying to demystify the data publication and access today. And now a further digression into organizational structure. This rather busy diagram has a representation of us as a research team with those 4 roles over on the far left. And CloudBank is central to this diagram because we're trying to emphasize that CloudBank is coordinating the research team and the cloud vendors, which are indicated down below in this lower center left as Amazon Web Services, Google Cloud, and Microsoft Azure, but there are, of course, other clouds as well. And then up at the very top, we have the National Science Foundation and other federal agencies like NIH and so forth. And then down at the mid right part of the diagram, we have programs that people can join into and participate in, such as NAIR and so on. So anyway, here's the layout of the diagram, trying to indicate that CloudBank is coordinating cloud access for the research team, and coordinating that with organizations like NSF. And the last thing I'll mention about this diagram is that when one thinks about cloud platforms, it's a good idea to bear in mind that not only is there the central set of services and technologies that that cloud provider has, but there are also a bunch of related services in what's called a marketplace that's associated with that cloud. So there's an Azure marketplace, a AWS marketplace, a Google Cloud marketplace, and these have technologies that aren't supported by the vendor, but they're associated. So things like Databricks and stuff. Okay. And then my last, I think this is my last digression slide, is to emphasize that CloudBank is really in the business of facilitating research. And we have these links. The portal is the main sort of way for a researcher or a prospective researcher to interact with CloudBank. And then we have learning resources and a community knowledge base, community.cloudbank.org. And then we conduct studies such as the one that I'm presenting in this clinic, or analysis of technologies like SkyPilot that was developed at UC Berkeley. So that's my quick run through of all of that. And now finally a diagram to get us back on track with today's topic, a diagram of the cloud for research ecosystem. So I think this is a click in. So there's first of all us again, representing a research team. And there's the internet, which is apparently a magenta stripe. And we're connected to the internet. And then there's the cloud, which is rather dominating in this diagram that I've drawn. But the cloud is also connected to the internet. And within the cloud, there is this profusion of services, which can be rather daunting, and we don't want to dwell on that too much or spend time learning things that we don't need. We'll continue onward. Also inside the cloud is something called object storage, which one can think of as an infinite capacity disk drive that has fairly quick access, particularly within the cloud. And you can attach a URL, or in other words, a web address to this object storage if you so desire. And I'll say more about that in a minute. And object storage is not associated with a particular virtual machine. So it persists on its own as a maintained system. And sometimes these are called buckets or blobs. Okay, so that's an important thing to sort of keep in mind as one learns about the cloud, is what object storage is. And then there's also a little call out to the spot market, which I mentioned earlier, which is a whole lot of virtual machines available at a drastically reduced rate. And to fill out this ecosystem, I'm just going to indicate that there's a technology called containerization that we touch base with the Docker Hub. And then there's GitHub, which is an online sort of source code management system. And that's also important for lightweight publication of resources, which we'll also get to. So now returning to today's topic, I wanted to talk about different ways of publishing data. And I have a total of 5 methods for publishing data. This is method number 3, which is public object storage, or wheeling your data out to the curb for anybody to use. So this is a screen capture of an application called S3 Browser. It connects to the Amazon object storage, what I just showed in the previous diagram. And it has sitting here some temperature data, some salinity data, oxygen data, and so forth. And what that is not important here to the narrative. Just the fact that this data is there, and each of these files is 16 megabytes. And you could just go here and download this with your own copy of S3 Browser. It's publicly available. So this is the wheel your data out to the curb approach. And if this is all you need to do, then you can do this. And you should be aware of the let's say, security implications. But if you're happy with that, you can do this, and there's your Science Gateway. You're done for the day, and you can skip the rest of this presentation. Okay, so this table I will not dwell on as a eye chart to read through all the boxes. I'm just going to mention the two highlighted in yellow sections, which are these are the 5 different ways that I can elaborate data publication, starting with the shoebox, which I could, tape up and send to my colleague. But method number 3 is cloud object storage. That's the wheeling your data out to the curb. And then the approach number 5 is what we'll spend the rest of this presentation talking about today, which is the NoSQL database plus a serverless API. So I'm squishing together all that jargon that I mentioned earlier. So data publication and access. Now we're back on track. Options beyond wheeling your data out into the street are, as I indicated on the previous slide, those other 4 methods. And so now we're going to persevere to using this idea of serverless, which is code that's developed in some kind of a development environment. We're using VS Code, and then deployed to the cloud where it runs. And we don't know how it runs, but we're confident that it will run reliably. And so we have these 2 examples. The simple one is courtesy of Naomi Alterman's walkthrough, and that is all about publishing a sparse/wide, in other words, many columns periodic version of the periodic table to the cloud. And each row of this table is going to have an identifier, which is going to be the name of an element, and then it's going to have a series of columns. And we can talk to this data system, this very simple data system, using a web browser. So here's an example query of the system, and it's asking for information on sodium. And then we'll, from the basis of the simple example, push on to the complex example, which is publishing data from a UW-based ocean observatory. And we'll access by an API, but rather than using a browser address bar, we'll use a Python code. And that's what gets us back to the just 2 lines of code to access the data without knowing any details. So the place to begin, if you happen to be reading through this deck or listening to this, is to start off with Naomi Alterman's MSE 544 periodic table walkthrough. That's a great place to begin. So this is what it looks like, and this is the URL. And what's great about this, let's see. Let me go back up here for a second. What's great about this is that if you were to go through these 3 modules, first of all, virtual machines and workstations, then NoSQL databases, and then finally serverless functions and APIs, and work the example and get this working on your own, you'll have a really solid understanding of how the pieces fit together, much better than what I can do in this Cloud Clinic presentation. So I'm touching on the topics, but this is actually the opportunity to do the work of really internalizing the process. And here I mentioned that we'll test this system by doing a URL in our browser. So this is a screen capture of the success. We have a pythonbytes.azurewebsites.net, and that just comes together in the process. But then we have a /API. I'm looking at the address bar up at the top. And so the address includes /API, and that tells the serverless function to go and look into the API information. And then it has a keyword lookup, where it's just called a route. And then we specify that we're interested in information about sodium. And what comes back is this sort of JSON-looking, or dictionary-looking, I should say, text describing all this information about sodium. So that's the example of the success of that process. And that allows us to pivot then to the complex example, which is, again, this road to 2 lines of code. So this is the sort of list of steps. You would first take the complicated data that you want to make available, and you would stage that in some kind of tabular format. you would then configure and preload that data into a NoSQL database that's on the cloud. So that NoSQL database, I have to emphasize, is offered as a service by the cloud provider. In the case of that we're working through here, we are using the Azure cloud, the Microsoft Azure cloud, and their database service is called Cosmos DB. So we'll be using Cosmos DB to implement a NoSQL database. And then we go off and we write and test a data access API. That's the programming interface. And we publish this as a serverless function. So as I mentioned before with the jargon run through, a serverless function is just some code that's going to run on the cloud, and it's going to run without us having to worry about what computer it's sitting on. It's rather magical. Okay, so once that code is running on the cloud, that's an API. So then we can actually test that API by creating something called a client. And that client is able to go and ping that API that's running on the serverless function. And it will in turn pivot over to the database that we created, pull the data out, and send that back as a response to that query. So then we can formalize that client as some Python code and publish that into a GitHub repository. And then our colleague can come along and do a git clone and create a copy of that from GitHub to their local computer, and they can use that code example to write 2 lines of code. The first one just imports a Python program that's got that has a useful function in it called chart. And then the second line of code is to execute oc.chart, give it a couple of parameters, and what will come back are some pandas data frames for those sensors, those ocean sensors that we mentioned. The first one is temperature, and the second one is salinity. All right. So that's an overview of the complex process, and this is the result of calling that chart function. So down at the bottom of this slide, this is the previous slide, is the oc.chart function call. And that's going to return some data, but in addition to returning that data, it's also going to draw a chart. So this is the chart that you get if you happen to run that. And here's some other examples of some additional charts. And you can see that the data are changing because each one of these represents about a 2-hour jump in time. So I'm going to take a moment to describe what we're seeing here, because this is oceanographic data, but what are the axes, right? And what do these 2 colors mean? So the basic idea here is that you have a sensor or sensor package, including temperature, which is going to be in red, and salinity or saltiness, that's in blue. And that's acquired by the sensor package that's raised through the water column from a depth of 200 meters below the ocean surface, all the way up to near the surface. So up at the top of this graph where it says 0 on the y-axis, that's the surface of the ocean. And that goes down 200 meters down to the bottom of the graph. And so the sensor, as it passes through this water column, and it takes about an hour to do that, measures both the temperature and the salinity of the water. And this is the plot that we generated of what that looks like. So if I go up, this is the previous example. And if I go down, this is the current example. And you can see that the structure, particularly the temperature structure of the water column, is changing every couple of hours. So we have this interesting data set. And I mentioned that we also get the data back. This is an example of the salinity data that's returned to the program. So not only do we get a pretty chart to look at, but we also get the numerical data as well. Okay. So how long would it take to learn how to do this stuff? For the periodic table, I'm being very conservative in my time estimates here, but basically it's setting it up is 2 hours, and then 2 hours to get the virtual machine, get a virtual machine running. We'll get into the details of this later on in this presentation, but the bottom line here is that by taking a non-recipe sort of figure it all out and understand it reasonably well approach, it's about a couple of days of work to go through this example and understand everything. And my emphasis is that after this time investment, one has a very good grasp of the process. Now, if one is new to cloud infrastructure, and this is all just amazingly complicated and perhaps daunting, some more time would be needed to build out some background. And if one is experienced with the cloud, you could probably go through this stuff in a day or faster. But the bottom line is that building a sophisticated, customized data system that's specific to your research needs would be a project that would take months. And we don't want to, sugarcoat that. It's definitely an investment in time. Okay, so this page is listing some resources. And these are all things that one can go and check out individually. Internet 2 has a division that's offering training on the cloud. That's a really good resource to know about. The basics of Git, Bash, and Python are covered by an organization called the Carpentries. Nexus, I'll mention more about in a second. I also wanted to emphasize that the browser search window is a great place to start in finding training resources. For example, if you were interested in becoming a infrastructure building expert on the Azure cloud, you can simply start searching on Azure training resources and you'll find all kinds of stuff. Same thing for the other clouds also. They want to make training resources available to you to make it easier to learn how to do this stuff. And then there's the Ocean client that I was writing those 2 lines of code. So if you wanted to see those 2 lines of code again, you can just simply make a clone of this repo. And it will automatically, it has the hard-coded URL of the data system that we're building. I mentioned something called Nexus. This is a side project of mine, but it's also on GitHub, so it's available. And the point of Nexus is for me to basically write down process notes for stuff that I'm going to come back to in 2 days and I'll have forgotten what I was doing. So it's how-tos and pointers and annotations and so forth. So that's just something I'll mention in passing as a potential resource. Let's see. We use the word scale to consider a Science Gateway project where you're interested in publishing data for access. So the word scale can be kind of vague, but in my mind, it particularly refers to the fact that more data is probably going to be acquired, and so your data system will have to grow, scale up. And then if you are doing a great job and your data is really of interest, then perhaps more and more people will be making use of it to power their models or what have you. So the community's growing data demand would be the voracity. So there's 2 aspects of scale that are relevant to considering going about building a data system. And then R1 just refers back to this idea that data is acquired in one format and then consumed in a different one. And so this raises the question of if you're going to build a science gateway and you're going to serve out data, do you try and anticipate the needs of your user community, or do you try and just keep things really simple and make the reformatting the data for use their problem? So this just gets into a really deep, interesting topic to discuss with your research team, how much effort is needed to get the data into a shareably useful format. So this table I showed earlier, this is just another copy of it. And the point here, again, not to belabor it, but the very bottom row here, which is the complicated example that we're talking about today, is a cloud NoSQL database connected to a serverless API. And flexibility is probably the most exciting thing about this because it's all put together using code, and that means that you can go back and change how you put it together in 2 months when you get some new ideas about how you want to change the way the data is served out. And there is the downside of there is this big time investment to learn. And then once you build a system on the cloud because you pay for it as you use it, it's also important to be able to track and pay for the cost that you're incurring. Okay, so now let's see. This is a recapitulation of the starting point, which is Naomi Alterman's tutorial modules on putting together the infrastructure for this data system, for this gateway. So here's how the remainder of today's presentation will go. So we have this complicated objective of serving out these interrelated data sets, the temperature and salinity, in a meaningful way. And the next thing that I'll do is I will review the basic build and collaborate structure. Sorry, the build process and the collaborating structure. Then I'll do a demo, and then finally there are some slides that are going to be details that we hope are of interest, and then we can see if there's any questions. So here's how it's done. This is the how to do it part of this presentation. Okay, the next slide is going to feature a researcher who is drawn in blue, and they are going to be building this data system. And they publish the data, and they publish an API to the cloud. So there's the cloud, and now it's got data in it, and it's got an API. And this is open to everyone. Then the researcher slash builder writes a client that is able to talk to that API, and they publish that example client on GitHub. So the client is something that anybody else could download and run that client, and it will also talk to that API. Then there's another person on the diagram who's in green, and that's their colleague. So they do exactly that. They download the client and they use it to explore the data. So the holy grail is achieved, that the green person is exploring the data without knowing anything about how the system is built. And this is a complicated diagram. So there's a simple version of this diagram that follows. But I wanted to identify sort of the locations, both real and virtual, that are involved in putting this data gateway together. Again, not to sugarcoat that it's simple, because it's slightly complicated. So the person on the blue is represents the researcher slash infrastructure builder, and that person has their laptop, which is indicated below them, which is running some applications like VS Code and maybe a Jupyter notebook, and they've got a web browser, and they've got a Linux bash shell up and running, and they're able to do everything that they need to do from their laptop. And the first thing that they'll do is set up an Azure account, since we're using the Azure cloud today. And that account allows them to log into something called the Azure portal, which has access to all these different services on Azure, including virtual machines or VMs, and serverless functions, and NoSQL databases, and so forth. And then hopefully they can also somehow track their spend there. So from there, they start up a virtual machine, which is at the top center. That's the cloud virtual machine. And that is running something called VS Code server. And that allows the person in blue to see what's going on that cloud virtual machine. And then everything proceeds from there. So that's kind of like a base of operations. From the cloud virtual machine, that person will go ahead and start up the NoSQL database and populate it with data that we're concerned with. Both temperature and salinity, and something called profiles. Profiles are metadata about when those sensors are being dragged through the water column to make measurements, and it happens about 9 times per day. Function apps is at the center of this diagram, and the function apps are serverless functions that run on the Azure cloud that listen to the internet. And when somebody sends a message, and we see the person in green on the far right, sending messages to the function apps, those are requests for data, which then come back, hopefully successfully, with the data that the green person is interested in looking at. Finally, the last thing about this is that the person in blue has created a client, and they have published it through the blue dotted line up on GitHub. That client is called Ocean Client, and it's sitting there minding its own business until the person in green gets wind of it, and they download their own copy of it, and they would run that on their laptop, and that's what's actually making the function app calls, the API calls to the function apps, and pulling the data back. And because the person in blue knew that the person in green would like to see a visual representation of the data, they included the chart functionality so that the chart is published there. And that's how that story all gets put together. I don't think there's anything else. So let's do this again, but in simplified form. So here's the previous slide one more time, and there's 5 locations for the guy in blue to worry about. Their laptop, the Azure portal, which is the gateway to all the Azure services, an Azure virtual machine or VM running VS Code Server, and then Azure functions, which are the serverless functions, and finally the Azure Cosmos DB, which is the NoSQL database. So the narrative is I use the Naomi MSE 544 tutorial to orchestrate these resources. In other words, I go to that tutorial and start following along. And when I'm done, I have a example that uses the periodic table. In the process, I learned how the end result, which is this data API, is constructed from data in a NoSQL database wired up to a serverless function triggered by HTTP requests. So I'm intentionally kind of repeating myself because I tend to go way too fast, and I'm hoping to do a good job emphasizing the central concepts of our narrative here. So once I've gone through the periodic table tutorial, I have enough of a context now to build out my own shoebox gateway and my own shoebox client that I publish on GitHub. So that's our story. Demo. Okay, so now at this point, I'm supposed to have a demonstration. Let's see if I can find my demonstration. Is that visible? Okay, I got a thumbs up from Naomi. So this is that client. Here's the 2 lines of code. I'll try and highlight that. First line of code is an import statement that just brings in the Ocean Client Python code, which has a function called chart. And the second line of code runs that function. So if I hit return, so this is a live demo. Let's wish ourselves good luck. About 6 seconds have gone by. Okay, so according to this, it took 8 seconds. And the query result was, in fact, a profile out in the middle of the ocean somewhere of both temperature in red and salinity in blue. So that worked out. And just for grins, here's another call of the same thing, but I've switched to the next profile in the sequence, recalling that there are 9 of these profiles per day. And that also is taking about 10 seconds or so. Okay, and that's run. And it's got a slightly different shape to it. So we're seeing the evolution of the upper water column. And then the last 2 lines of code here, these are data structures that were recovered when I ran the previous line of code. So up here we have DFT, DFS. Those are data frames of temperature and salinity, and that's what's returned by the charting function. Kind of mixing functionality here for the sake of economy of expression. And that's what the temperature data table looks like. And likewise, the salinity. So that's that. Voila, the demonstration. And this, by the way, is what the client code looks like. It's about a page and a half or so of code. And it has built into it hard-coded. That's not necessarily, well, anyway, hard-coded is the serverless function URL that hosts the API. Okay, so hopefully I'm returning now to our main presentation. And as I said, after demonstrating the sort of how it's done and that it works, lastly, we have some details to go through quickly. And that will do it for today's presentation. So the first detail I want to point out is that the temperature and salinity data are acquired by something that profiles its way through the upper 200 meters of the water column. And this is a time series of 2 days of the profiler depth. So you can see that the profiler is sitting down at around 200 meters, and then it has these jagged upward to the near the surface and then downward excursions. And so the timing of those excursions is not regular. And so one of the things that's happening when we do the 2 lines of code is it's actually going to the system and finding out when the profile happens so it gets the right block of data so that it's not just all the sensors huddle at the bottom where they're parked in between profiles, but it's the actual ascent profile. See, I'm going to skip over that. Um, Maybe I'm not. Well, I will just say that on the topic of NoSQL, we're suggesting it as a interesting and flexible means of hosting data. It's possible to use other approaches to data hosting, particularly SQL, but I think I don't want to try and go down that road too much with discussing ACID. ACID, I guess I'll say, take a moment to say that ACID is an acronym that refers to the stability and reliability of a database. And it's particularly important when you're building a system that has both people reading to and people writing from, no, writing to and reading from a database, where you want to make sure that the transactions that are happening are coordinated so that there isn't like collisions happening between two mutually incompatible activities. And this kind of durability, let's say, is supported both in the NoSQL world as well as in the SQL world. This is historical, the sort of history of NoSQL. It starts here at 1998, but my understanding is that NoSQL really started to take off around 2009 or so with the advent of an open NoSQL data system called MongoDB. So just a little bit of background on NoSQL. And then I said that there's a few more details, so we'll just cruise through these last few details. This particular detail has to do with building and testing an API. And I mentioned that we're using the VS Code application or development environment to do that. One thing that's really nice about this approach, using VS Code, running on let's say a virtual machine that we're logged into, is that we can not only build the API, but we can test it locally inside of that virtual machine. And we're doing that using this localhost alias and some port forwarding. But the point is that I'm now testing my profile API on a machine by using localhost to make sure that it works the way it's expected to. And then once I've done that, then and only then do I publish the API to the cloud. So the next slide shows that same API call, but this time it's being executed on the Azure cloud, on the function application, and then it's getting back the same data. So it's a two-step process. First, test it locally on the virtual machine, then publish it to the cloud and test it there. I mentioned that the cloud portal is one of those sort of 5 locations that we have to mentally coordinate as we're getting into the process of building. This is an example of the Azure portal in action, referring to a virtual machine. That's the magenta arrow at the upper left is showing the virtual machine access. This is the Visual Studio Code application running. And some of these circles are being used to emphasize different aspects of using this environment. And I think I will just charge ahead here because with the details at the end of this talk, I don't want this to drag on too much longer. This is another Azure Database Service detail. So again, we're in the Microsoft Azure portal, which we visit through a web browser, and we're selecting the Azure Cosmos DB. And this is actually a screen capture on the building a database process. The Cosmos DB is the service. Within that, we're going to select a NoSQL subtype of database and use the Create button to build that. And then once that's built, we can click on Go to Resource, and that will take us to the database that we built. So this is indicating navigation through the process as outlined in Naomi Alterman's walkthrough. And then finally, this is the Azure portal in all its glory, directed at the NoSQL database. So there's a number of features here. First of all, there's the data service that I've allocated called Rob's Data Ocean. And within that, there's a database called Oceanography. And within that, there's a container or a table called Salinity or OSB Salinity. And within that, there's a list of items, and this is the actual data. So at the far right, we see timestamp, depth, and salinity. So that's where the data is being held. So let's keep on going here. Last couple of details before we wrap it up. First of all, the API that we built is in the business of handing back data, but somebody else who wants to use it might be interested in how to format an API call. So this is a little bit whimsical, but it's a demonstration of calling the API by just asking for info. So at the top, we have this sort of yellowish address bar, which refers to oceanography.azurewebsites.net/API/info. And info is saying, give me some information about this API. And the rest of the text is what comes back in response, and it tells you how to write code that will query this API and get profile information. Okay, and then this is an example of a very simple client. It says instead of like a page and a half of Python code, this is a 3-line client. The first is to import the request library and then use that to hit the Azure websites.net info, and then it prints out the same message. So that's illustrating the transition to Python coding of a client. Okay, so this is instead of hitting the API to get info, this is actually hitting the API to get a profile for day 5 and index 4. That's profile number 4 out of 9. And there's the information coming back. I had an amusing thought, which is I could try and teach the API to test itself, but I found out that there was sort of some terrifying possibilities for recursion there. An API that calls itself could end up doing so ad infinitum, and then we'll end up down the rabbit hole. So upon sober recursion, I believe API testing is better done by something other than the API itself. Little coding philosophy from a non-computer science person. This is a reference to the MongoDB storyline, better explanations of NoSQL and so forth. The world of documentation is there waiting for us. So that's everything that I wanted to say. Again, we appreciate you following along with this. And my general polemic is that open science is worth some consideration of the effort. Cloud technology is really built for enterprise, for businesses. And here as scientists, we're taking advantage of that to do the thing that we care about, which is publishing data for open access. And in short summary, the API that we build is running in a serverless function that's tapping into a NoSQL database. This deck will be made available, and here's the important link to Naomi's walkthrough. For reference, if you have questions or issues with CloudBank, the help desk is help@cloudbank.org. And that's everything. Thank you very much.
Thank you, Rob.
Well, yeah, very much our pleasure.
Yes, so, well, I really get a good lesson on how to share the data in a more secure way. We used to, well, I'm a computer science PhD student from University of Idaho. So we used to interact with the API, and we download a lot of data set from some open API portals, but we never think about sharing our data set that way. We used to maybe share our data on GitHub repo, but we
Hmm.
haven't think about using the Azure server to do the do these kind of things. I'm wondering that if I can still gain the access to these slides, so I can access to the code is shared in the slides.
Yeah, I believe you can see the slides now.
Yes, I can see it. I'm wondering if you will cancel the sharing after the presentation.
No, no, no. I'm going to leave it there.
Okay, good to know.
Yeah.
Thank you. Appreciate it.
Yeah, absolutely. Thank you so much for dropping by.